This section is about hyperbolic sine function, hyperbolic cosine function, and their inverse and their derivatives. Okay, I just like trigonometric functions, so we focus on sine, tangent, and secant. Okay. And here we will do the similar thing. I'm trying not to cover all the functions because most of the time when we test you, we focus on the three functions: hyperbolic sine x, hyperbolic tangent x, hyperbolic secant x. Okay, so let me give all the definition. Those are not brand new functions. They're just defined using, yeah. They're just defined by those formulas. Hyperbolic sine x is just e to the x minus e to the negative divided 2. So it's nothing new here. And here you get the sum of that. So you probably don't need to introduce new functions, but in some problems we find that's convenient, and so you can use that. Hyperbolic tangent x is going to be, just similar to the trigonometric functions. It'll be sine hyperbolic sine x and over hyperbolic cosine x. Okay, you can also express it in terms of e to the x. Okay, and hyperbolic cotangent x will be just upside down. Okay, now we also have the hyperbolic cosecant x and secant x. Secant x is 1 over hyperbolic cosine x. Hyperbolic cosecant x, 1 over hyperbolic sine x. So those are the functions we are going to study. And what are the basic properties we have? We are interested in hyperbolic sine x, right? And the tangent x and the secant. Those are the three functions. Okay. But we do have similar formulas, like the derivative of hyperbolic sine x, right? When you differentiate, you just differentiate e to the x, right? E to the negative x. So what you get here is e to the x plus e to the negative x. Then you're surprised this is just hyperbolic cosine. It's very similar to the derivative of sine x equals cosine x. Okay, now there's a difference. If we differentiate hyperbolic cosine x, right? Then when differentiate, you will e to the x still get e to x. E to the negative x with negative e to the x. So you get hyperbolic sine x. Now there is no negative sign in front of hyperbolic sine x. This is some difference. Okay. And maybe you can look at the derivative of hyperbolic tangent x and also hyperbolic secant x. There's just too many formulas. But you can, if you forget it, you can derive it. Okay, you can derive it by yourself, because if you know hyperbolic sine x, the derivative and the derivative of hyperbolic cosine x, you can find the derivative of hyperbolic tangent x. Okay, it should be similar to the trigonometric function, maybe different by sign. Okay, the derivative of hyperbolic tangent x, my guess, should be equal to hyperbolic secant square x, because we have a similar formula for the derivative of tangent x. Okay, but we do have a formula similar to the formula in the trigonometric geometry. This is a plus equals 1. Here's a minus. Okay, you can verify this identity from the definition. Using that, you can, let's do the exercise, all right? Find the derivative hyperbolic tangent x if you forget that. Then how do you differentiate? Use a quotient rule. Okay. Use a quotient rule, you will get, this is a derivative of hyperbolic cosine x cosine x, right? By the quotient rule, what do you get? Hyperbolic cosine x squared. Then the derivative of hyperbolic sine x become hyperbolic cosine x. Then you have something coming from the denominator. Then you minus the derivative of the denominator times the numerator. So you get this. And then that's the numerator. Numerator becomes 1. And this is nothing but by the definition of the hyperbolic secant x. So those are the formulas you can easily get it by yourself if you only memorize those two. If you only memorize those two formulas, you can get the formulas for the derivative of what, like even, you know, hyperbolic tangent x, derivative hyperbolic secant x. Okay. This formula I have here, also if you divide both sides by 1, by cosine x, right? So divide this identity by hyperbolic cosine x. You get the 1 minus hyperbolic tangent square x equals, see, this is again another similar formula. You can compare with the formula in the trigonometric geometry. Okay, using this formula, yeah. So this is one formula. This is another formula. Those are two formula equivalent. Okay, so those are the formula you can get. Okay, now we're going to talk about the inverse function. All right, let's look at hyperbolic sine x. So hyperbolic sine x is a graph. Okay, how do we sketch the graph? This is a e to the x minus e to the negative x. So if you draw this graph, can you quickly draw it? Well, you needed to know a few key things, right? So when x equals 0, right? So y is going to be 0 too, because when plug 0 for x, you get 1 minus 1 in the numerator. That's the first thing. Second, you get when you put a negative hyperbolic sine x, well, it will be negative sine x. So that will be the other function. So the graph of the other function will be symmetric about the origin. All you have to do is to get a graph for x greater than 0. So for the graph for x greater than 0, how do you draw it? Starting from 0, right? Then I think it's the increasing function. It's going to be increasing. And then gradually it will be almost equal to half of, yeah, when x is sufficient large, the second term e to the negative x is almost equal to 0. So look at this. It's going to be you take e to the x out, right? So this is almost equal to e to the x for large x, right? Half of e to the x. So it's increasing function. Okay. So you can get a asymptotic behavior of the graph. And then since it's symmetric about the origin, so the other graph must be looked like that. So clearly this is a graph, it's increasing and it has inverse, right? Now if you don't, if you can double check the derivative is hyperbolic cosine x, which is always positive, right? So it's increasing. So the function, the increasing function, and the inverse exists. Now, what is the inverse? Okay, so you can solve for x in terms of y. So this has a solution. You can solve that. And very lucky this time, since hyperbolic sine x is expressed in terms of e to the x. So the inverse, we find out it's not a brand new function. It also can be expressed in terms of other known functions. Let's do it, okay? So it's a good exercise. We're going to solve this equation in terms of x. Solve for this function for x expressed in terms of y, right? So I want to get this formula. Okay, let's try it. Well, y equals e to the x minus e to the negative, right? So how can I solve for x? That's good exercise for the logic function, right? So you multiply both sides by 2. Okay, it's 2y equals e to the x. Then what? I still have x on each side, right? In two terms. I multiply both sides by e to the x. Okay, I got twice y e to the x equals e to the 2x or e to the x squared minus 1. Okay. Then this is actually is a quadratic function, e to the 2x minus 2y e to the x minus 1 equals 0. So this is a quadratic function in e to the x. Now if you let u to be e to the x, then you get u squared minus 2y u minus 1 equals 0, right? It's a quadratic function. It's pretty standard technique. Then you solve for u. Once you get u, you can get x, right? Not plus 1? Why have the plus 1? Because I move all the term to the right hand side.
Oh, you mean to the right.
Yeah, the right hand side is negative 1. Yeah, because x e to the 2x is on the right hand side. All right, so let's solve for y. Solve for u. Okay, it's 2 negative b plus minus b squared minus 4ac. Okay, so you put the details there, you get 2y plus minus 4y squared plus 4 divided by 2. I can take 4 out of the radical, so I get just y plus minus y squared plus 1. Now, I know u is positive, so I cannot choose a negative sign because y minus square y squared plus 1, the second term is right, so it'll be negative. So since u is going to be positive, so I have to choose that place. Okay, since u equals e to the x is positive, okay? So that's only one solution. All right, so now u equals this. So x is going to be natural log of y plus square y squared plus 1. Okay, so we get, this is nothing but the hyperbolic, the inverse of hyperbolic sine x. All right, so we actually get this formula for the inverse. The question is, how do you find the derivative of the inverse? Okay, I'm not talking about other functions. Let's focus on this, and the rest of them we just, either do as exercise or we can just memorize the formulas. Okay, it's a similar idea. You get you have the inverse function for the hyperbolic cosine x. Yeah, so also for the tangent x. Okay. All right. Question: how do we? Question: yeah. What is a derivative of? The graph. Okay, let's look at the graph first. Yeah, so y equals hyperbolic inverse hyperbolic sine, okay, which is going to be natural log of x plus square root x squared plus 1. Okay, how do you draw the graph? X is I think it's arbitrary, so the domain, the range will be the same as will be from infinity. Okay, so this is a graph for the original one, right? Hyperbolic sine x. So you draw the line, middle line. Right. Then let's use a red pen. Then I think this is a graph of y equals inverse. Okay, so the range and the domain is still the same from negative infinity to positive infinity. Never, don't worry about it. My question is, how do you find the inverse? What is the best way to find the inverse as a derivative of the inverse? Okay, this is our exercise we're trying to find. Okay, okay, find the derivative of this. Okay, there are a couple ways to find out the derivative. Either you use a formula already. We have a formula, right? You can use a formula to find the derivative, and you can also, if you're able to solve for the inverse function and express it in terms of elementary function, you can differentiate directly. But sometimes the formula is complicated, right? Then another way to find the derivative is using the formula we already learned. Okay, the formula we already learned is, let's look at two methods. The first one, using the derivative formula, okay, which is going to be the derivative hyperbolic sine x, okay, right? That's the formula, right? Hyperbolic sine, now we have 4 letters, S, I, N, H. Just like somebody's last name, you can search on the internet, you can find it maybe. Okay, I'm pretty sure there's someone with the last name, S-I-N-H. Okay, so we use the 4 letters for the name of that function. Usually we just use the F, right? Remember F, right? Yeah. F, derivative of f of x equals 1 over f prime, then parenthesis f, the inverse function. Yeah. All right, so this becomes cosine h. How about cosine? I guess if there's such last name, must be a, let's say Indian name, S-I-N-H. I just guess. Okay, I saw some names similar to that. All right, S-I-N-H. Okay, so now, very similar to the trigonometric functions, can we use more elementary function to express this? Okay, right? How to do that? Well, in trigonometric geometry, we use a triangle for formulas, right? But you can also use a formula here. Remember, hyperbolic, right? Something square, right? Minus, this is a hyperbolic sine. There are a couple ways to simplify, okay? I'm trying to not to use the formulas for the inverse function. All right, so this is a nothing here. We don't put anything here, right? So this is always equal to 1, no matter what you put there. So if you put hyperbolic sine x here and there, right? And here you get, what do you want, right? Right, square. But this one is just x square. Why? Because hyperbolic sine x and the inverse of hyperbolic sine x put together just cancel out. So just x, okay? So if you move this x squared plus x, it's going to be x squared plus 1. But since you have to get rid of the square, so it's a square root of that. Okay. Now, why it's not negative? Because hyperbolic cosine is always positive. All right, so we solve this. And then we put back, we get the derivative of hyperbolic sine x is going to be 1 over square x plus 1. So this is a very interesting formula. And in the future, if you see an integral like that, and you immediately you can put the constant here. But you can also write it like this, right? It's x squared plus 1 plus c, because the inverse function is nothing but the natural log of x squared plus 1. Okay. All right. So that's the first method. What is the second method? Second method just differentiate directly, okay? Because you know that this is going to be, right? So you just differentiate directly, right? And you end up with the same answer, okay? That's good exercise. Differentiate directly. When you differentiate, okay, what is natural log? First of all, you have to put everything into the denominator, right? And then you have to differentiate the derivative of natural log is just 1 over something, right? Then you have to differentiate x squared plus 1 plus it. So that's the first step. Right. Next step. And here be 1 plus square x squared plus 1 over x. Now, how do I quickly get that? Well, the derivative of x squared plus 1, use a chain rule, you will get this, okay? X over square x squared plus 1. And the derivative of x is 1. So add them together. Now, how do you simplify it? Yeah, how do you simplify it? Yeah. So from here to here, you think about, okay? If you have time, double check, okay? So how do you simplify it? Well, you combine those two terms together, you will get square x squared plus 1, square x squared plus 1, and plus x, right? Then clearly canceled out. Then you end up with the same simple answer. Okay, here you just differentiate the inverse function directly, since you already have the formula. We also have, yeah, let me list all the other formulas again. Okay, what we got here is hyperbolic, the derivative of the inverse of hyperbolic sine x. Okay, x squared plus 1. But if you define the inverse function of the hyperbolic cosine x, then the derivative is going to be that. So this is a different from the trigonometric geometry, because when you add them two together, they are not going to be 0. Okay, in the derivative of the inverse of cosine x would be negative of 1 over 1 over x, whatever, right? So it's different here. Here we have a negative sign inside the radical. So you're not able to add them together. You're not able to cancel them. Okay. And the next one will be this. Okay. All right. So those are the 3 formulas. In the book, maybe you also have the formula for the derivative of inverse of hyperbolic secant x. Okay, we we probably don't need it to here, okay, at this moment. So let's do some exercise, okay, from the book. Okay. So if hyperbolic tangent x equals 12 or 13, okay, find the value for hyperbolic sine x and hyperbolic cosine x. Right. All right, how do we do that? Well, we use the identity 1 minus hyperbolic tangent x squared. This should be equal to hyperbolic secant x squared. Hyperbolic secant is just 1 over cosine, hyperbolic cosine x squared, right? So you already know the value of hyperbolic tangent x, then you can get the value of hyperbolic cosine x. Okay, so it's 1 minus 12 over 13 squared equals, okay, and we do have a very special Pythagorean theorem here. I hope some of you know this result. Okay, if this side is 13, this side is 12, this side is 5. Okay, it's a right triangle. Yes. Everybody knows that 3 squared plus 4 squared equals 5 squared. That's a more special. There are other special right triangles with integer lengths. Okay, this is one of them. That helps you quickly do the computation because this side is going to be 13 squared here, 13 squared minus 12 squared, which is just 5 squared. Okay, it's a 5 squared over 13 squared. Okay, so that means 1 over hyperbolic cosine x is going to be 5 over 13. That means hyperbolic cosine x is going to be 13 over 5. Right? Hyperbolic cosine x is always positive, so don't worry about that. And then you have another formula, you know, hyperbolic cosine x squared minus hyperbolic sine square x equals 1, right? Using this relationship, you can figure out hyperbolic sine x, right? So hyperbolic sine x squared is going to be minus 1, right? Which is going to be 13 over 5 squared minus 1. And then again 5 squared, 13 squared minus 5 squared, and that gives you 12 squared. Now the question is, what is the sign of hyperbolic sine x? Hyperbolic sine x is the same sign as tangent x, so it's positive. That's why I have 12, 5. Why this is have the same sign? Because you have this, right? Okay, this is a positive. Okay, remember, this is going to be 12, 13, it's positive. And this is a positive, right? So that means hyperbolic sine x must be positive. Okay, so that's the reason you only take the positive sign for the hyperbolic sine x. Okay, so we're trying to get familiar with these formulas for hyperbolic sine x, cosine x, tangent x. Okay, using those examples. Okay, as the next example, that will be we know this is an integral Okay, how to evaluate this integral? Well, when you look at this, it's clearly you have to use substitution, right? So step one, you let square x, right? Then du equals the derivative u with respect to x and dx, right? And the derivative of square x with respect to x is nothing but this. And this is pretty standard. All right, so now we go back to the integral. Square x becomes u, and x over dx, right? X over dx over square x is going to be 2 du. Okay, so it's just 2 du. Now, what is the entire derivative of sine hyperbolic sine u? That would be hyperbolic cosine. Okay, it's hyperbolic cosine. But that's not the end, right? So you have to replace u by square x. So you get this. So it's about the original function, not the inverse. Okay, so the next one. Now, if you are given, yeah, let's put the 4 here. Okay, so if you are given integral like that, you have to do a simple substitution, because we know that this will be, right? So we know that. So the slightly different here is that this is the one, other side is 4. So you have to modify, you have to let x to be 4, let's say 4u, okay? Or 2u, because 2 squared is going to be 4. Okay, then, or u is going to be half of x. Okay, then this integral, then du dx is going to be 2 du, right? Then you plug into the formula, you get 2u squared here plus 4, and the dx is 2 du. So finally, you get 4 u squared plus 1. You take a 4 out, it would be 2 du. That's 2 cancelled out. Then you end up with a similar integral here, and so it's u plus c. And what is u? U is half of x. Okay, so that's. Okay, slightly different problem. It's the integral of square root of x plus 1 and square x dx. Sometimes it's written in the form like x squared plus x dx. Okay, it's hard to figure out, right? X squared plus x. Yeah, I'm not sure we can evaluate this. Let's try, okay? Let's see. I'm going to. Okay, let's see if we, sometimes we probably cannot. I forgot whether it should be numerator or denominator. Let's do this. Okay, so the natural substitution is you let u to be square x. Okay, right? Right, you see the square x. So du is going to be this. Okay, that's pretty standard. So the integral, above integral, you will get x is going to be u squared. Okay, then dx over x is going to du. Right? So you transfer that above integral into this form. Then dx over square x is going to be 2 times du. And x becomes u squared. So you will get 2, right? Hyperbolic as the inverse of hyperbolic sine x, sine u, right? And plus constant. Since u is going to be a square x, so just put this. So that is the answer. Okay. Now let's spend some time to understand the inverse hyperbolic index. Okay. Remember, this is going to be e to the x minus e to the negative x, e to the x plus e to the negative x. So it's defined for all x. The question is what is the value of this possible value? The range of the function. Now, when x equals 0, it's going to be 0. But yeah, where's my file? So let's understand this. Trying to sketch this graph. It's not easy to sketch it, right? So when x equals 0, clearly y is 0. So it's passing through the origin. And it's also odd function because the numerator is the odd function, denominator is even function. So it's an odd function, okay? Odd function, okay? So that means the graph will be symmetric about the origin. All you have to do is draw the graph on the positive side, okay? Then you look at how does x, when x approaches infinity, right? So y equals, you take e to the x out. So you take e to the x out, you get 1 minus e to the negative 2x, and x 1 plus e to the negative 2x, right? So if you rewrite it, you will get, and clearly this is always less than 1, but approaches 1. So two things. This is always less than 1. So this approaches 1, right? As x approaches positive infinity, right? Because the numerator and denominator is e to the negative 2x. This approaches 0. Okay, so that's why the quotient is going to be, the quotient approaches 1. All right, so based on this information, I can sketch the graph for the function that is a horizontal asymptote 1 and the negative 1, right? So graph passing through the origin, so it goes like that. Right. It's increasing, maybe concave down on the right-hand side, concave on the positive side. So this is going to be hyperbolic tangent x. Now the inverse, I think the inverse exists. So you technically, you can solve for x in terms of y. I think you can solve it, okay? Now then you find the derivative of this. But what is the graph for the inverse function? The graph for the inverse function, you need to draw a line in the middle, then you I think this is my graph, okay? So this will be y equals, okay? Now, be careful about the domain. Domain for the tangent inverse of this, right? So the domain will be between -1 and the +1 because you have a 2 vertical asymptote, okay? And the y value is from negative to +infinity, okay? But for the tangent, for the hyperbolic tangent x, right? X is between -infinity and +infinity, but the y value is between -1 and +1. So they're just switch. Okay. All right. So the next step is to find the formula for the derivative. Okay. What is the derivative tangent x, hyperbolic tangent x, and what is the derivative of hyperbolic the inverse, right? The derivative of the inverse of hyperbolic tangent x. Okay. So we know that the derivative of, okay, this derivative, we already did a computation. It's going to be, it is going to be hyperbolic secant x, right? So let's find the derivative. It's a good exercise, right? Find the derivative of the inverse function. According to the formula, right, we have this. And then you get this, right? So how can I simplify this? We have a formula, right? So we have a relation between 1 secant square, right? It's hyperbolic secant square and put prime, right? So that's a formula. So if we put this into here, and this side 1 minus x squared, this side is, right? So it's not too bad. So immediately you will get this formula. Okay. And this is holds for x less than 1, okay? Because the domain of the inverse function is from -1 to +1. So in other words, if I put the integral on both sides, I get this, and plus a constant. I haven't give you a formula for the inverse function of hyperbolic tangent x yet, right? I'm pretty sure this can be also expressed in terms of a natural log. I remember, right? We remember the formula for the inverse of hyperbolic sine x, right? We did this, right? Recall that. Right? So my question is, what is this? Okay? Can we express in terms of x? It's possible, right? But I do get a lot of, using I know the derivative. Okay? I find I find out the derivative is simple, right? Even I don't know the expression for the inverse of a hyperbolic tangent x. So can you evaluate this without using the inverse function? If you are given this problem, can you evaluate this integral? This is math 165 problem. Okay, you can do that. How do you do that? Well, 1 over 1, right? Is going to be 1 minus x times 1 plus x. And this is, it's nothing but, okay, add them to get separate. You can use you can decompose it. But when you add them together, you get 1 plus x plus 1 minus x. 2x cancel out. So there is you have to divide by 2. Okay, I can quickly give you this identity. This is identity. Okay, 1 over 1 minus x squared can be decomposed. So then what? Then you put the 2 natural log. Now you can put the integral, right? Right? Now, every term here is linear in the denominator. So the antiderivative of 1 over 1 minus x is actually going to be, what is that? I know the second term is definitely 1 plus x, okay? And plus constant. The first term, is it going to be 1 minus x here? But that's one sign, negative sign is missing, okay? When you differentiate, you get 1 over 1 minus x, but you also get a negative sign. So that's why you have to put a negative sign in front of it. All right, so now you can combine them. Well, so that means let's compare with this formula, right? So you get 2 formulas here now. Okay, we also get a formula, right? This may be the different constant, okay? But actually this turns out the same constant. You just look, then what? Then you find out that hyperbolic inverse hyperbolic tangent x is probably just equal to half of the natural log of 1 plus x over 1 minus x. My claim is it is. They're all related, okay? So this is, and you can check when x equals 0, both sides is equal 0. Natural log of 1 is 0. Okay. So we use the derivative, we also end up with this formula. But can we prove that directly? The answer is yes, okay? Let's look at this formula, right? Okay. I'm trying to solve it for x. Solve it for x. Can you solve it? It's not a problem. Okay. Algebra, right? So you multiply both sides, you get e to the x plus e to the next y. In mathematics, as long as your computation is correct, no matter which way you derive, and you will end up with the same kind of conclusion. Okay, you will not get a contradiction. Okay, if you happen to get a contradiction, 2 different approaches to get the inverse function, then somewhere, some approach, there are some mistakes. Okay, so now we multiply both sides. I think I multiply both sides by e to the x. Okay, I got e squared, e to the x squared plus 1, y, e to the x minus 1. Then I collect those terms. Okay, great. I will I probably move this term to the left hand side. Okay, so I get I'll move one to the right hand side, not into the left hand side. Okay, so I get 1 plus y equals e to the 2x minus e to the 2x y. Okay, if I take e to the 2x out, this is 1 minus y. All right, so now it's pretty clear. It's going to be 1 plus y, 1 minus y. And what I'm going to do, I'm going to solve for 2x. Just put the natural log on both sides. Then I divide by 2. Right? So this is my inverse function. Right? This is nothing but the inverse of hyperbolic tangent x, tangent u, tangent y. Yeah. So we conclude that we get exactly the same identity as we did before. No matter which approach. Here, different approaches here, right? Different, and using this formula, you can also find the derivative. Okay, there are, no matter where you cut, where you get in, and you from there you do the computation, and you will get other formulas. Okay, so compare this with above identity, right? We already have one here. Inverse of hyperbolic tangent u, tangent x is going to be half of natural log 1 plus x. And how do we get that? We use the integral. We use a derivative. The derivative, the inverse of tangent x equals 1 over 1 minus x squared. Okay, how do we get that? We use another formula. So they're all, then from here, you can also find the derivative using the formula, right? So you can find the derivative, okay, using the above formula. And you end up with the formula you already got, okay? Since, yeah, the derivative of this, right, is going to be the derivative of half of. Now, how do you find the derivative of this? And like today's quiz, similar, the first problem. Okay, it's the first problem on the quiz. When you differentiate natural log of a very complex expression, don't do it directly. You have to modify the function. Okay, what do you have to do? You modify the function natural log of 1 plus x lined up. This will be much simpler. Okay. Then you differentiate each of them. The first one is 1 plus 1 of x. The second one is, right? Then there's a negative sign here. Okay. There's a negative sign, okay, negative 1. Where's negative 1 from? It's from the derivative 1 minus x. So you get this. But if we combine them, it's nothing but 1 over x squared. 1 over 1 minus x squared. So you get the same derivative we did using the derivative inverse function formula. See, let's go through the logic, right? Let's quickly go through the problems. Okay. So you have the hyperbolic tangent x. You know the inverse exists, but I was not in a hurry to find the formula for the inverse function, but I still want to find the derivative. Then I use the formula for the derivative of the inverse function. Then I get 1 over hyperbolic secant h squared and tangent. Then I try to use another formula similar to the Pythagorean theory. Then I end up with 1 over 1 minus x squared. And I use that. I got the integral formula. But then I look at the left-hand side. This is 1 over 1 minus x squared. It's a very nice function. I can even evaluate without this formula. I can evaluate directly. How do I do that? I decompose 1 over 1 minus x squared into 2 parts, linear, right? So the the reciprocal linear term. Then I can quickly evaluate the integral and get half of the natural log of 1 plus x over 1 over minus x. Then I get this formula, right? Then then I conclude that the hyperbolic tangent x inverse function must be equal to one half of that. I got this formula from the integrals, from the derivatives, not directly from the original definition of the inverse function. But I'm trying to check. Then I solve for x in terms of y. Then I solve it using basic algebra without derivatives. And I find out, yes, x equals half of the natural log of 1 plus y over 1 minus y. If you interchange the variable, then you get the formula again. Then use this formula, you find the derivative. You end up with 1 over 1 minus x squared. So it's like what is chicken first or egg first? It doesn't matter. Okay, you get an egg, you get a chicken. You get chicken, you get egg. Okay. Let's take a quick.